Okay, exam 2016. Finally got onto the breakdown of classical physics questions, which is always lots of, so let's do those. 15. In a calibration experiment, light of any wavelength less than 241 nanometers and with intensity I is established to be able to produce a photocurrent at a detector plate when illuminating a metal surface in a vacuum. The detector plate is held at a voltage of plus 1.2 volts with respect to the metal surface. Again, that means that any electron that's emitted will end up at the detector plate because it will be attracted to it. Now, a series of 3 new lamps are then used in the apparatus. Lamp X has a wavelength of 243 nanometers and in 36 times the original intensity. Longer wavelength, right? That means lower energy. Okay? So each photon has got less energy. There might be a lot more photons, you can see that there, but each photon has less energy. Lamp Y has a wavelength of 103 nanometers and intensity a thousandth of the initial intensity. Each photon, shorter wavelength, a lot more energy, so these are very much more energetic photons, but there's a lot less of them. Lamp Z has a wavelength of 203 nanometers and an intensity of 0.04 I, right? So again, slightly more energetic photons, right? And a fair few less of them. The lamp which will generate a photocurrent in the experiment for a detector plate voltage of plus 3 volts R. Oh, okay, which lamps? Right. Now again, it's a positive voltage, so provided they can emit a photoelectrons at all, they'll be fine. Now note, we've established that light of any wavelength less than 241 nanometers does. This presumably means that anything greater than 241 nanometers doesn't, because if anything less does, then obviously anything greater doesn't. So lamp X is no good, but both lamp Y and lamp Z have shorter wavelengths, so they'll be fine. D. Okay. Next. Oh god, I hate Compton scattering. It's so hard. I'm going to be guessing here. An X-ray beam of wavelength lambda is directed along the x-axis in the positive x direction and is incident on a carbon target. For X-rays scattered at an angle to the x-axis of pi radians, an electron is produced with momentum component in the x direction of. Okay, I don't hate it so much. Alright. Oh, yes I do. Oh, I do. I hate it a lot. So what we have is we have an X-ray coming in, hits an electron, and afterwards we have the electron is now travelling along like that, and the X-ray has been scattered through pi radians, it's going straight back. Okay? So now initially our X-ray has a momentum of h on lambda. If it didn't lose any energy at all in the collision, then it would return with the same momentum, h on lambda, the same lambda, and then the total change in momentum of the X-ray photon would be h over lambda plus h over lambda, and that would give us the momentum of the electron. Alright? Now, however, when our X-ray photon comes in, that is its momentum. When it goes back the other way, its momentum is going to be slightly less because the wavelength will have got longer, it'll have lost some energy to the electron, so it'll be lambda plus something. So let's look at our formulas here. It says h over lambda plus h over lambda plus something. That looks promising. This one says h over lambda minus h over lambda plus something. No, H over lambda plus H over lambda minus something, no. H over lambda, no, no. Yeah, it's the first one. It's that, okay? Came in with this momentum, left with that momentum, and the sum of those two momentums ends up with the electron there. Beautiful. That was so easy. If you go and actually stick the formula in, you'll get that. Pete's questions are often like that. So many questions. If we do good questions, they're like that. They're like, hey, I don't even need the formula if I know what's going on. Okay. Now, a beam of laser photons, each of energy 12.094 electron volts, is passed through a dilute gas of atomic hydrogen, causing the formation of excited hydrogen atoms. Assume the Bohr model applies. The quantum number of the laser excited states is. Okay. So, the thing we have here is we have that the energy of the nth level is 13.606 over n squared, negative thereof. Okay. And so we have gone from minus 13.606, the ground state, up to some state which is 12.0494 electron volts higher. So let's do that. Minus 13.606 plus 112.094. So this energy level is minus 1.512 electron volts. Okay, so we've got to use this formula here to see which number corresponds to that. So let's try 4. Okay, so 13.606 divide 4 squared equals, no, too big, let's try 3. 13.606 divide 3, x squared equals, yep, minus 1.51, yep, beautiful, so 3 it is. That's our answer. This stuff is easier than I thought. Next, in a vacuum, a metal surface of work function 5.2 electron volts is illuminated by UV light of wavelength 210 nanometers. A detector plate is held at a voltage of plus 2.8 volts with respect to the metal surface. What is the maximum kinetic energy of electrons reaching the detector plate? Well, we feed in a certain energy given by that wavelength. We lose that much energy because that's how much energy is needed to get the electron out of the metal surface, and then we add this much energy because the detector plate attracts the electrons because it's got a positive voltage. So all we need to do is convert this one here, 210 nanometers, to and we use E equals hc over lambda. Do we have the value of h? Yeah, 4.136 by 10 to the minus 15. 4.136 times 10 to the minus 15 times 3 times 10 to the 8th over 210 by 10 to the minus 9. Quick calculation says 4.136 exponent minus 15 times 3 exponent 8 divide 210 exponent minus 9 equals, so this gives us 5.91 electron volts. Okay, so, or just 5.9 because this is so 5.9 electron volts we supply. We lose 5.2, which gives us 0.7 when we get out, and then we add 2.8 because this is positive and attracts the electrons. So 2.8 plus 0.7 is 3.5. Beautiful. Right, 19. A positively charged particle of mass m is trapped in a one-dimensional region of potential U equals 0 volts and width A on 2. Outside this region, the potential is infinite. Boom, boom, boom. A over 2. Okay. trapped. In the ground state of the system, what is the wavelength of particle and the energy of the state? Okay, the ground state is like a closed pipe. It is like this. Lambda is equal to twice that. So 2 times A on 2 is just equal to A. So get rid of that, get rid of that. Right, what about the energy? Well, I've forgotten this, but of course P equals H on lambda. Right, that is mv equals H over A in this case, because lambda's A. So m squared v squared equals h squared over a squared. Divide both sides by m, and we get mv squared equals h squared over ma squared. Take a half of that, and we've got to take a half of that, and we get that the kinetic energy is a half h squared 1 over 2 ma squared, something like that, yeah. H over 2 ma squared, h over 8, go for D. Right. Useful formula that, got to remember that all the time. Okay, next moving on to blackbody radiation. Now, in an experiment to study a blackbody radiator, the intensity of emitted radiation is measured as a function of the wavelength. At a particular temperature T1, the wavelength of the highest intensity radiation is determined to be lambda 1. When the temperature is changed by delta T, the wavelength of the highest intensity radiation changes to lambda 2, with lambda 2 being 0.9 lambda 1. The relationship between T1 and delta T is, oh God. Okay, there's the joke answer, not possible to determine because of the ultraviolet catastrophe, right? But now, I'm going to try and do this without the formula. Look, I know that lambda max times T is equal to a constant. That's in the formula sheet. So what we've done here, we have lambda 2 is shorter than lambda 1. This is smaller, therefore T2 must be bigger than T1. And since that's 0.9, in other words, so we have lambda 1 T1 equals lambda 2 T2, and lambda 2 is 0.9 lambda 1, therefore T2 must be T1 over 0.9, because it has to equal that still. So, yep, T1 over 0.9. So T2 equals T1 over 0.9. Oh, however, that's not what we were asked. We were asked delta T, okay? So delta T is T2 minus T1. Oh, yeah, equals T1 over 0.9 minus T1 equals 1.1111 T1 minus T1 equals 0.111 T1. Therefore T1 equals 1 over 0.111 delta T, and that's equals 9 delta T. Oh God. Go for B. Yeah, look, on yeah, in this instance, if I had time, I'd probably actually just stick a couple of values in and see what I got. It's rather messy. You can hate Pete for that, it's his fault. Alright, moving right along. if the wavelength of a photon of energy E is lambda p, and the wavelength of an electron of kinetic energy E is lambda E, then the ratio of the wavelengths lambda p over lambda E is what? Okay. I can rule one out. See this one? It's got the mass of the proton in it. It's not that. Okay, well, shouldn't be too hard. Okay. Energy of photon. Energy of photon is equal to HF, which is equal to hc over lambda. Yeah? So that's the energy of a photon. Right. Now, that's the photon. That's lambda the photon. Energy. Now for the electron, we have P equals H over wavelength of the electron. That is mv electron equal mv equals H over lambda E. Do the usual thing, square it, n squared v squared h squared over lambda E squared. Take an me over here, put in a half, and we get that the energy of the electron is equal to h squared over 2 mass of the electron, wavelength of the electron squared. Okay. Massive. It doesn't matter if it's massive proton or massive photon, it still doesn't work. Okay, so coming back here, we want to have the wavelength of the photon over the wavelength of the electron. So we need to write this one as lambda E squared is equal to, put it over there, h squared over 2me E. Take the square root. And that's equal to h over square root of 2me E. Lambda p from here, lambda p is equal to h c over E. Okay. Therefore, we're asked for lambda p over lambda E is equal to hc over E over h over the square root of 2me E, and so h's cancel and I get c times the square root of 2me E over E, which is equal to c square root of 2m over E. I'm really unhappy about that. So look at the answers and see if any of them look approximately right. Oh yeah, 2mc squared over E. You can see that this there, c over times the square root of 2m over E is actually the same as that. Yeah. Oh my god, that is awful. Okay, we've got there. Alright. Okay, consider isotopic ion lithium 2+. 3 protons, 4 neutrons and 1 electron. So it's a standard single electron atom, so it works like a Bohr atom. The energy required to excite this ion from the ground state to the first excited state is closest to. Okay, ground state E1 is equal to minus z squared over n squared times 13.606, and that is equal to minus 13.606 times z squared, which is 3 squared, divide n squared, which is 1 squared, equals minus 122.45 electron volts. Alright, the first excited state, E2, is equal to, right, doing that, it's going to be minus 3 squared times 113.606 divide 2 squared equals minus 30.61. From that we must subtract the ground state, minus 122.45, and we get 91.8 electron volts. So we have to add 91.8 electron volts to the ground state to get to the first excited state. Beautiful. Okay. After a Compton scattering event, the electron has the maximum kinetic energy when the photon scatters through an angle of, think pool balls. If you have 2 pool balls, if this one comes in like that and goes back like that, that'll give the maximum energy to this one. 180 degrees, done. Piece of cake. Okay, in an infinite square well potential of width d, the de Broglie wavelength of the trapped particle is d on 2. What is the quantum number of this state? Okay, so n equals 1. N equals 1, lambda is 2d. Okay, n equals 2, n equals, that's 1, n equals 2, lambda equals d. N equals 3. Oh god, I can't even draw it. N equals 3. It's going to go, how does it go? Yeah, that. 3 lambda equals, well, 2/3 is, that's one wavelength, is 2/3 of d. 2/3 of d. And it's obviously going to be n equals 4. N equals 4. The next one I'm going to draw, that will be one wavelength to there and a second wavelength to there, and so its wavelength will be half d. Yeah. N equals 4, done. I think. Yep, we're on to waves and optics.